Yeah, so the speaker is, oops. Yeah, today we have the speakers from RISE, Miguel, Pietro, and the second presenter is Agnese Attanasio from CETMA, and the last presenter is Michele Zanini from FenX. So now I would like to start the webinar. So Miguel will start first. So the floor is yours.
Oh, thank you, Nate. Sorry for the technical issues. 1 second. We're having some issues. So yeah, let's start from the beginning. So I will present. Well, my name is Miguel Prieto, and I'm working as a PhD in civil engineering in RISE Research Institute of Sweden, and I'm working with cellular lightweight concrete for the last 5 to 6 years. I will talk about cellular lightweight concrete as insulating material, a way to a fully mineral concrete sandwich panel solution. This would be the outline of my presentation. So I will talk first about the iClimabuild project and about our role in the project. So iClimabuild project is a project called Functional and Advanced Insulating and Energy Harvesting Storage Materials across climate adaptive building envelopes. And it's an EU-funded project with a 4-year duration between 2021 to 2025. So we are like a little bit past the middle part of the project. It involves 27 different partners from 14 different countries with a budget of 16.4 million euros. The project is related to the Open Innovation Testbed Concept, or ITB. There's an entity offering access to physical facilities, pilot lines, capabilities, and service required for the development, testing, and upscaling of nanotechnology and advanced material for new innovative products and services in industrial environments. The project works towards nearly zero emission buildings in passive technologies for reduction of energy demands and active technologies covering remaining energy needs. We'll take a little bit of time to present RISE Research Institute of Sweden. It's a research institute in Sweden, and we are working in the Department of Infrastructure and Concrete Technology, and myself in the Material Design Unit. We work in research and development projects in different fields like plant chemistry, applied concrete technology, structures and durability, recycling, 3D printing, and dynamic injections. We do characterization, consulting, and certification and regulatory framework. Here is the team that works in iClimabuild. We are placed in several places in Sweden, southwest Sweden, Borås, Gothenburg, and Lund. And we have interdisciplinary expertise with geologs, chemists, engineers, and material scientists. What we do in iClimabuild project. So we are part of Pilot Line 4, cement and concrete-based materials for wall facades, and we are working together with HTWK, TUD, and TUHH. RISE is working with prefabricated cellular lightweight concrete and CLC with aerogels used as insulating material within sandwich wall facade panels with layers of textile reinforced concrete. We are involved in 2 test cases, test case 3 and test case 4, that I will explain a little bit later in the implementation, that have been placed in several living labs like CUBE in Dresden, UECAT in Manresa, and HIEQ Polito in Milan. So what is the motivation for cellular lightweight concrete as insulation material? So construction sector is moving towards sustainable construction. By 2050, new buildings shall become energy neutral and have zero CO2 emissions. And as you may know, energy consumption in buildings represents 40% of the total energy budget in the European community. So In that sense, the envelope design, materials, and construction type affects the comfort and energy efficiency levels of buildings. And the building envelope insulation is crucial for an energy efficient and comfortable indoor environment and accounts for around 50 to 60% of total heat gain loss in a building. So there is a growing demand for new solutions concerning the energetic retrofitting of buildings, and these solutions should be energy efficient, fire safe, as well as promoting healthier indoor environment. Some rough numbers: in 2025, insulation market will achieve 35,000 million square meters, being thermal building insulation around 60% of this market share. So that's why we want to work with cellular lightweight concrete as insulation material. So what it is cellular lightweight concrete? It's also known as foam concrete. It's a lightweight concrete with densities that can range from lower than 100 kilos per cubic meter, that this is the topic I will address today, to 1,800 kilograms per cubic meter. So the low density of CLC is obtained by air voids created by mixing foam agents in mortar. So what is foam concrete or CLC? It consists of a mix of binders, cement mainly, sand, water, and a preformed foam created by mixture of compressed air, synthetic surfactant, and water. So how we do it? So we mix the mortar. We create the preformed foam with a foam generator. We introduce it and mix the mortar with the foam. And finally, we obtain the CLC, the cellular lightweight concrete or foam concrete. So CLC has an homogeneous structure with void sizes that can range from 0.1 to 1.5 millimeters in diameter. The CLC properties are closely related to the as-received density, so the density that the material has in its natural humidity. So you can see here two different properties. So one is related to the compressive strength and versus the density, and you see that the compressive strength ranges like from 10 kilopascals to almost 1.75 megapascals, depending on the density. The same applies with the thermal conductivity. So between 50 to 250, we can have quite a range of thermal conductivities. So this is highly dependent. All other properties like sound absorption are also related to the density. So what are the applications of CLC? They depend on the density, as I was saying. So between 100 to 600 kilograms per cubic meter, we mainly see thermal, acoustic, and fire protection applications. So they are non-structural. From 600 kilos to 1,100 kilograms per cubic meter, we normally see bricks, blocks, and non-structural elements, and higher densities up to 1,800 kilograms per cubic meter. We have structural applications such as precast walls and slabs. Talking about a little bit the properties, so CLC fresh state has a flowing and self-compacting rheology, as you can see in the GIF, and it has an excellent workability. If we talk about the insulation material that we are addressing today, the CLC insulation block that you can see here. So for the densities that we are achieving that are around 90 kilograms per cubic meter, we have a coefficient of variation of 10% and a compressive strength of 30 kilopascals. This compressive strength is similar to conventional EPS type 11. If we look into the thermal conductivity of this material, so for the densities that we are talking about, the CLC thermal conductivity is 0.036 watt per meter per Kelvin for this ultra low density. So to keep in context with other insulating materials such as EPS has range from 30 to 40 watts meter Kelvin, or XPS or rock wool. So the CLC is in the range of these materials insulating properties. We have also worked with aerogels from the University of Hamburg. And as you can see here, in the green dots, the thermal conductivity of CLC with 50% of aerogels by mortar volume was similar to the CLC that we are working, that it is in red dots in this figure. Talking about fire resistant, CLC insulation increases fire safety in sandwich panels. So it's a class A1 material. If we compare to organic insulating materials such as polystyrene and polyurethane foam, they are highly flammable and release toxic fumes during the fire. And inorganic materials such as mineral wool, although non-flammable, have a large embodied energy. Talking about the environmental impact of the insulating material CLC, it has a lower environmental impact compared to organic insulating materials such as polystyrene with similar insulating properties. So here we have this table where we compare the material that we are working in iClimabuild with 36 watt meter Kelvin, 0.036, and EPS, and with a global warming potential per cubic meter of 54 compared to 78 of EPS, and an embodied energy of megajoules per cubic meter of 99 versus 2000, around 2000 megajoules. Also about recyclability. So here you can see that we are working also in recyclability. So what we do after casting the CLC, we crush it and sieve it, and we obtain the material that it is below 63 microns. So to try to use it as an SCM. Here we can see the cumulative heat versus time of a R3 test. And we can see several densities of CLC without heat treatment and with heat treatment, and the comparison with siliceous fly ash. So the first results show a similar reactivity as siliceous fly ash, at least until 72 hours, and slightly less at 168 hours. As we can see also, reactivity of the recycled CLC can be improved by thermal treatment. So this is without thermal treatment, and this is with thermal treatment. And also, we will continue this study to verify the initial results and implement it in new CLC insulation blocks, so that we have a circularity of the material, complete circularity. So then implementation, about implementation in iClimabuild. So we have worked in two test cases. Test case 4 is related to a sandwich panel with two whites of 30 millimeters of textile reinforced concrete, as you can see here. So these are the two whites, and an insulation layer of CLC and also CLC with aerogels of 210 millimeters, with a calculated U value for the sandwich panel without voids, without openings of 0.17 watts per square meter per Kelvin. This is a collaboration between HTWK, TUD, and TUHH. So we produce the insulation material, and then HTWK produces the complete sandwich panel using the fibers from TUD, and TUHH is providing to us the aerogels that we implement in the CLC mix. So this test case 4 has been and will be implemented in 3 living labs: CUBE in Dresden, EURECAT in Manresa, and HTWK Prieto in Milan. So you can see here the production facilities that we have at RISE, and we casted CLC and CLC with aerogels in a planetary mixer with 350 liters of capacity. Some pictures of the casting process of the different insulation blocks and the curing, and then finally a picture of a video from Manresa, EURECAT Manresa installation at their facilities in the living lab. Then I will talk about also test case 3, that it's related to implementing an autonomous in situ wall insulation humidity monitoring sensor, TEG, developed by Technology. In this case, the pilot line is related to the sensor, and Bryce helped to produce the textile reinforced concrete and the CLC and install the TEG sensor that it is now installed in the living lab of Cube in Dresden. And so far, we have promising results from this sensor. So the goal is here to have some sensor that can be autonomous. And some final summary and conclusions from the cellular lightweight concrete material insulating block. CLC insulation can be an affordable insulating solution for achieving near zero energy buildings. It's as sustainable as I have shown and recyclable alternative for organic insulation materials. And the CLC has similar insulating performance, 0.036 watt per meter per Kelvin, as existing insulating materials such as EPS, XPS, and rock wool. Compared to organic materials such as polystyrene and polyurethane foam that are highly flammable, CLC is non-flammable and therefore increases fire safety of the concrete sandwich panels. Also, CLC has a lower environmental impact than existing insulation materials such as EPS and a slightly lower cost. So we have accounted for a cost of around 50 euros per cubic meter for CLC insulating material. Also, as I have shown you, CLC insulation can be recyclable and could be used as an SCM, a supplementary cementitious material, as I was showing by this R3 test with initial promising results. And this will allow concrete-based sandwich panels to be fully recyclable. And just to finalize, I wanted to share with you that in the context of another EU project, like Cook, that has been finished already, it was identified by the Innovation Radar. It's a new Commission initiative that has identified RISE and the CLC insulation incorporated in a load-bearing sandwich panel as a high potential in innovation. So yeah, this is all from my side. If you have any questions, just let me know.
Yeah, now the audience can ask the presenter if you would like to ask either by Q&A or you raise your hand and then I will, you can ask directly. No question from the audience? I have one. So has CLC launched already in the market or not? And do you have a plan of for selling this on a, about this material?
In the market is not yet, and we are in the process of patenting it. So we are gathering all the necessary things to put it into the market. So yet we are not having anything in the market. It's just that this former project that we have a industrial installation in Italy, and and now what we have in the living labs in HTWK build project. But yeah, we are in the process of trying to patent it and sell it.
Okay, yeah. Any question? If no, we will move to the second presentation. So Agnese, you will start, right? Yeah.
Yes, good morning, everybody. Michele, can you please share your screen with the presentation? Just a moment. Okay, thanks a lot. Good morning, everybody. let me introduce this second talk of this webinar today. Today, we will talk about recycled materials used to produce a sustainable building solution, insulating in sandwich form, basically. I am Agnese Attanasio. I am a research and development engineer at CETMA in Italy. And in this work, in these activities, in this presentation, also Michele Zanini, CTO from FenX, Switzerland, will present and is collaborating with me and our group for this innovative solution for the building sector. I would like just to introduce my group. Okay, who we are. CETMA is a research and technology organization. We work basically in the sectors of applied research, experimental development, and technology transfer in specific sectors, basically in the advanced material sectors, but we also work on the product development and ICT. What is our specific expertise in the construction sector? Our group, our area, works on the development of innovative solutions for the construction in the perspective of a circular economy, but we also work on structural monitoring and diagnostics of buildings. What is our role in the iClimaBuilt project? This is an European project we are working with in collaboration with a lot of partners, as it was referred during the previous presentation. Our role in this project, we are basically CETMA and also FenX. We are leaders of a pilot line, and we are also responsible for the development of materials and components for the building sector, starting from recycled materials. CETMA is also involved in performing some tests to characterize the materials, but also the components.
Right, from my side, hi everyone, as Agnese very kindly introduced myself as well. So I'm here on behalf of FenX. FenX is an ETH startup. We are located very close to Zurich, Switzerland, and our mission is to transform low-value materials, preferably also waste, into high-performance, safe, and sustainable materials for the building industry. And our specific expertise nowadays, we focus on mineral boards, so mineral foams for insulating buildings. And the role is to collaborate with several the consortium. We consider with several partners, and particularly our main focus is connected to insulation components incorporating mineral waste.
Okay, here you have, you can see a general, the topics of this presentation. We will talk about circularity and construction industry. We will talk about sustainable and insulating materials. And after this part, we will talk about some innovative materials we have developed in this project in collaboration with FenX. And specifically, we have worked on lightweight concretes and mineral foams, CETMA on the first material and FenX on the second material. And after that, we will show you some options to combine these materials produced in sandwich solution suitable for innovative building construction.
Right. So tackling the problem from a macro perspective, we wanted to start this by thinking about circularity and the construction industry. So we know that globally the building stock area has a huge growth rate, comparable to the living floor of New York City. So essentially, we are constructing on a monthly basis the same stock area of New York City. On the other hand, we have to acknowledge the fact that we do not always construct buildings that are designed to last centuries, right? So we have some examples, and the fact that I'm presenting with Agnese from Italy gave me opportunity to, to bring here an example of the Colosseum in Rome. But we also know, and it's very recent, that is an example from UK, and you can read the news on The Guardian, that in some cases, in that particular case, was concrete that was literally crumbling. So several schools in UK had to get closed in September, the beginning of the new school year, because they are unsafe. Literally, they are falling apart. So as you can realize, we are constructing a lot, but we are not planning to deconstruct, and that's probably a weak part of the entire building industry. And in this way, somehow we are probably missing 50% of the business, right? So the point here is that the building stock is very often not designed to last forever, right? And we are at the same time, we are not providing material traceability, and therefore is extremely difficult to deconstruct, and very often deconstruction ends up in landfill, where everything is mixed, and is extremely difficult to then source back raw materials.
Okay, so this is another important topic when we work when you work with the construction sector, the building materials. An important aspect is to make these materials more and more sustainable. We can start just from one consideration, one important consideration. The construction of building requires a lot of materials. 50% of the European natural resources are used for the construction. So you know that this is basically a problem. So we have to move in another direction. The construction industry needs to become more sustainable, and needs basically to reduce the use of materials which are non-renovable materials. So a modern construction, to be considered modern, as main challenge is we have to choose materials that have less impacts on the environment, and we are involved. We have to develop materials and products, methodologies which are more sustainable. Basically, what is a sustainable construction? We can consider a construction sustainable when we adopt materials and products in building based on the use of less natural resources, and we have to increase the recycling also of materials and also products, and in parallel, in that way, we can also reduce the wastes. So it's important, as everybody knows, to recycle waste materials to enhance the sustainability of the construction industry, and it's important to follow basically what is called the circular economy approach. We have to turn waste into new resources, and at the same time to reduce the impacts of wastes on the environment. You see in these figures basically what is the approach of circular economy. You have different steps. You start from the manufacturing of a building. After the consumption, the use of materials, components, etc. You have basically two ways. You can you can basically produce waste, or you can decide to use this waste and recycle them to convert them in new resources, and to introduce again these materials in the loop, so to manufacture, to build new solution again for the building. And this is basically the sector where we are trying to work.
Right. So on one hand, of course, circular economy principles are extremely important, and on the same line of thinking, we also think how we can also deal with how we construct, right? And particularly insulating materials is a very interesting topic, since, as Miguel already presented, 40% of the worldwide energy consumption comes from buildings, so is required to the operation and embody energy of buildings. And very surprisingly, the majority, 60+%, is due to heating and cooling cycles. So in that regard, it becomes extremely clear that insulation is one of the top solutions on how to reduce the energy requirement of buildings. So in this particular case, insulation can tackle both the operational energy by, of course, insulating, so by decreasing the dissipation of heat in cold and in warm environments. And if the insulation is per se also sustainable, it also contributes in somehow dematerialize the building itself, and therefore to reduce the embodied energy of the building itself. So here, insulating materials are a top solution to reduce the impact of buildings.
Yes, okay, after this introduction where we have tried to explain how important it is to work on materials for the construction sector which are sustainable and also insulating, let's move now to describe our main outcomes about the materials we have developed in this period, in this project, in collaboration also with FenX. CETMA basically worked on, as I mentioned before, on the lightweight concrete development. Some basic info about the lightweight concrete. This is a concrete having a reduced density. This is below 200 kilograms per cubic meter, in contrast with a normal weight concrete. So due to this reduced weight, the main property of this kind of material is that these materials are thermal insulating materials. So these are very interesting in order to improve the insulation of buildings where these kind of materials are installed. What is the way to produce this lightweight concrete? Basically, we have two options. We can work producing bubbles of gas in the cement paste. This is the case of the foamed concrete, as referred during the previous talk today. The other option is to replace dense aggregates used in concrete, partially or totally, with lightweight concrete. So basically with lightweight aggregates. So basically with the aggregates having less density in comparison with normal weight concrete. Apart from the sector of the lightweight concrete, our main goal is also to work on concretes which are sustainable and also green, to produce materials with less impact on the environment. So how we can produce these green concretes? Basically, we can start from recycled materials. So we can basically work on aggregates, on alternative binders, or combination of them. In this case, in this specific case, we have worked on aggregates. We started from recycled aggregates. Examples of aggregates used are aggregates from construction demolition waste. You know that construction demolition waste are available in huge volume. These represent more than 1/3 of waste produced in Europe, and in terms of composition, they are almost composed by minerals, so concrete mortars, bricks and tiles, glass, etc. Another kind of aggregate which is studied is coming from waste plastics. You know that we have a lot of waste plastics. These are commonly this landfill, but these materials can be converted in new aggregates and used for the development of innovative and sustainable construction solutions. In the next slide, I have just presented some photos of this concrete we have produced in this project. This is a lightweight concrete fully based on recycled aggregates. These aggregates are in part from construction demolition waste, which have been used as normal weight aggregates, and this has been combined with plastic aggregates coming from waste from different sector. In these photos, you see on the left our concrete in the fresh state, and on the right, you see some samples of this concrete after curing. Each of these samples is allocated to specific tests, since we wanted to validate what are the performance of the materials produced in terms of mechanical, thermal properties, durability, etc. In the next slide, I have collected in a table the main properties of this sustainable concrete. In the fresh state, the workability is S5. This means this material is very fluid, so can be used to for casting operation in different typologies of framework. So it's very easily to be casted. In terms of density, this is below 100 kilograms per cubic meter, so this is a lightweight concrete. In terms of compressive strength, this is in the around 3.5 megapascal, so this is a non-structural concrete. Thermal conductivity is 0.23 watt per meter Kelvin. Also in terms of durability, this material performed very well, since the performance are stable in terms of mechanical performance, and also thermal performance after several cycles of freezing thawing. So on the right, you can see a photo of some panels produced with this concrete. This is basically an insulating concrete. In terms of mechanical performance, it has moderate mechanical performance. So again, this is a non-structural concrete, but the main property is that this material is a sustainable material, since it's really based on recycled aggregates. Okay.
Right. So do you want to add something, Agnese? Sorry.
No, it's okay. You can
Right.
describe the other material. Thanks.
Right, exactly. So the first part of the material provided by CETMA is lightweight concrete. What we are focusing at FenX are mineral foams. So as one of you for sure knows, foam are dispersion of bubbles, of gas bubbles into a matrix. If the matrix is plastic based, then classically is a plastic foam. And if the matrix is inorganic by nature, then very often the foam is referred to mineral foam. So mineral foams in a more fancy manner can also be considered as a mixture of rocks and air, right? And here you can see a literature example of a mineral foam where the matrix is a mineral, and the voids are the bubbles. And very interestingly, as also Miguel showed in a former presentation, you can also observe from literature that the porosity and its size distribution is extremely important to eventually determine the thermal conductivity of the porous article. So the higher the volume of pores, the lower thermal conductivity. So, and for having insulating materials, it means that we have to introduce a lot, but really a lot of gas, right? So the porosity can go very quickly beyond 80 and 90 volume percent. So there are several ways on how to produce mineral foams, and within this project, FenX explored the possibility of creating the so-called cakes, so larger elements. So we compounded powders and liquids, we foam them, we cast them into molds to create the so-called cakes, and then we slice those cakes to create panels, right? And then over time, the properties of the material evolves, right? And recalling the concept explained before, the target of FenX is to cover a region of interest that not necessarily is covered. So in terms of in a diagram where we can plot the thermal conductivity against the embodied energy, very often we can find extremely good thermal insulators which have an embodied energy which is extremely expensive. On the other hand, materials that are less conductive, very often they also have associated less energy during production. So in this diagram, you can see that by increasing the porosity, you can increase make the thermal conductivity lower, so you can increase the insulating performance, as discussed in the former slide. And then to reduce the embodied energy, there are several tricks how to select the material, and also the process, how you do manipulate with kind of temperature, what kind of in general treatment do you use. So it's a question of processing and material, which are extremely interlinked. And as I said, FenX is trying to capture and to cover, so it's aiming to explore this uncharted territory in thermal conductivity and embodied energy. So particularly for this project, we focus on developing materials for two main installations in living labs. So FenX is active in a test case 5 together with CETMA, and the test case 5 has been applied in Amposta, in the living lab of Amposta, and in the near future will be installed in Dresden, so in the living lab called Cube. And for that reason, two different formulations has been selected. On one hand, we had a compressive strength of around 250-300 kilopascal, and a thermal conductivity of around slightly below 50 milliwatts per meter Kelvin. And then we develop a more insulating solution for the test 5 for Cube, where the compressive strength is lower, so is around 80 kilopascal, and the thermal conductivity is below 40 milliwatts per meter Kelvin. Particularly here, we measure around 37, 38, and then I round it up to 38. So particularly now, I give the floor to Agnese to explain one solution that we developed within this project.
You are muted, sorry.
Okay, I'm here. Okay. Okay, so after the optimization of these two typologies of materials, on one hand a lightweight concrete and on the other hand an insulating foam, the idea was to combine these materials to produce some innovative sandwich solution for building application. Of course, we started from specific targets, requirements, so we started from considering that the components to develop have to be installed in specific living laboratories in Spain and also in Germany. We started from the geometry required, from the maximum weight, the performance required, especially in terms of thermal performance, since our components has as main feature the thermal insulation of buildings. We started from these requirements and we designed our solution, which are, as mentioned before, intended for insulation of buildings, new or existing buildings, and can be used for external or eventually also for internal partition walls. In this scheme, you see the two materials, so the lightweight concrete and the foam panel produced in two parallel pilot lines. These materials at a certain point are combined to produce two kinds of sandwich solution. One is a thermal block and the other one is an insulating panels. Basically, in this kind of component, the insulating part is done by the foam layer, which is very light in weight and very insulating. And for the concrete, which is used for the two external layers, apart from the insulation, the main role is to straighten the structure of the component produced. In the next slide, I will show you something about the thermal block. We have already produced and installed. We have produced full blocks and also half blocks in different dimensions. In this photo, you can see the two typologies of blocks produced. So in the core side, we have the core part, we have the foam. The external layers are made with concrete. The total thickness is 30 centimeters in both cases. On the right, you see a figure where you see, okay, the internal part, so the foam and the concrete. What kind of a component is this? This is an infill component for walls. This is a self-building component, and the intended use is for thermal application. In the next slide, I have just collected the main properties of the materials used. So the lightweight concrete and the mineral foam used to produce this kind of component. So you see that okay, these materials have completely different density, compressive strength, and thermal conductivity, which are there is a sort of compensation. Since basically the mineral foam is the most insulating element, and the compressive strength is basically done by the lightweight concrete. In terms of performance of the block produced, in the photo you can see some blocks produced. We are below 500 kilograms per cubic meter. The thermal transmittance for 30 centimeters of thickness is 0.22 watt square meters per Kelvin. This is on a single block without plaster, and the weight is not so high, so this kind of element can be easily moved in the construction site. In the next slide, you see the installation of these blocks produced in Spain. So you have basically an external facade, first floor, in this living lab in Spain. This is our way to prove that this kind of solution can be installed in a Mediterranean climatic zone, and currently I think they are under monitoring to see if the thermal performance are in line with the expectation. Okay.
Right. So on one hand, we had the thermal insulation block, where the layers of the lightweight concrete were around 5 centimeters, and on the other hand, we wanted to provide a slimmer solution, right? And as a line of reasoning was the standard way on how to install panels, especially for compact facades or so-called ATICs, right? So in a standard manner, and this is very often done with EPS or potentially also with wool solutions. So panels are cut to size, and very often this happens on a job site. They are glued on the wall, and then in some cases they can be level, especially in terms of in case mineral materials are used that are some inequalities in the thickness can be leveled off. And then very often panels and I would say all mineral panels are then mechanically fixed to the wall, and then the wall is reinforced and finished, right? So this is the line of thinking of the market and how the market want to deal when you have to insulate external walls with panels. So in that line of thinking, we're taking inspiration from that, and we're trying to make, as I said, a solution slimmer than a block by essentially reducing as much as possible the lightweight concrete outer shell, and ideally in a future step also removing one of the two layers, right? So in this particular case, we are targeting the living lab in Germany, in Dresden, it's called Cube, and the combination of materials will lead to a density of around 350, 360 kilograms per cubic meter of the overall block, and in this case we can go lower than 0.2 in U value on a single component. And this is something extremely interesting for the climatic zone of the Central Europe. So this brings us to conclusions, and I leave the floor to Agnese for that.
Yeah, I will conclude this talk with a few considerations about the work done so far. It's clear that the circularity is the main challenge in the construction sector. So to do this, we have to work on secondary raw materials in order to produce novel, sustainable materials for this kind of application. It's important. Another important aspect is to produce solutions which are insulating, since the insulation has an important impact on the heating and cooling efficiency of buildings, and is also connected with the energy savings in buildings. From our side, our work was based on this idea. The rational combination of materials from recycled sources is an important element to move in the direction of sustainability in the construction sector. Basically, our contribution is based on the development, as described before, of an innovative, sustainable lightweight concrete and an innovative insulating foam elements, starting from waste materials. These materials have been produced and validated and also combined to prove that this can be used for the manufacturing of innovative sandwich solution in the form of a thermal block, which has been already manufactured and installed in Spain, and an insulating panel, which is under production and is allocated to a living lab in Germany. In general, we can say that our solution can be, of course, further modulated, implemented, depending on the specific target applications on the performance we would like to have finally. In the last slide, you can see just our contacts in case you want to talk with us about these aspects, but in any case, we are here for any question. Thanks for your attention.
Okay, thank you very much, Agnese and Michele. Do you have any question, the audience? No.
So I see Carlos who put up
Yes.
a hand.
I tried to check. Okay, I will see. Sorry, wait a sec. I try to unmute, allow mic. Yes.
Hi, good
Yes.
morning. Thank you. Thank you so much for allowing me to make the question. So
Yep.
my name is Carlos Ochoa. I'm from the International Energy Research Center here in Ireland. And my question is related regarding the pre-processing of these materials, because as you mentioned, the lightweight concrete has is from recovered concrete. How do you consider the separation of waste material that is not useful, that could be harmful for the concrete, and if this affects the final cost of the whole block compared to ethics, for example? Thank you.
It's not clear if the question is for the concrete or for the ethics, so I don't know if this is something I can answer, or
It's for the concrete.
Yeah, it's for the concrete. So you're referring to the separation of materials, you mean?
Yes.
But before the production of our concrete, and after the production of our concrete solution?
Before the production.
Yeah. Okay, so in this case, we have basically used materials which have been already separated, let's say. We started basically from construction demolition waste from local sources, of course, to reduce the cost, of course. So our work was, okay, we started from the mineral fraction directly. Our work was just the separation in to have the right side for the aggregates we needed in the concrete. So we started basically on CDV, W minerals, and our work was just to separate in the proper side to use this material as aggregates. So this was our activities mainly. We have not separated CDV in, I don't know, minerals, plastics, metals, something like that. I don't know if I have answered.
Yes, the other part was how does it affect, for example, the cost compared to, say, because the end is an insulating concrete, but then how does it compare to a normal product that would have been made from new materials?
So you mean a comparison between this kind of concrete and
yeah, in terms of cost?
Others in terms of cost, of course, as you know, when you produce new materials in the first period, of course, the costs are not, it's not easy to compare the cost with something which is already on the market. You need more time to develop your solution, and maybe in some years, your solution can have costs comparable with other solutions on the market. We are not on the market. This is just a work resulting from our research activities. So for the moment, we cannot say nothing about the cost, but we imagine that over the time, the cost will be more affordable. This is my view about that.
Okay, thank you.
You're welcome.
Yeah, and I see the question from Achilles. If I'm sorry if I pronounce it wrong, but what is the TRL of the presented sandwich panel, and will it be ready for actual production when finished the project? And have you compared them with commercial products in terms of characteristic and possible cost? So it's more or less kind of similar to the other question as well, but yeah, you can answer.
Right. So here I probably pitch in since I took the lead on the panel part. So the TRL so far I would say is relatively, I would say 4 or 5 because it's still in the lab, and then we will have a jump in this project to around, I would say 7, since we will expose in a living lab, so to a relevant environment. I would say at the end of the project should locate around there. It is, I would say, the first step towards a real market acceptance validation, right? Which should be done anytime soon when we start collecting information on how technically is valid our solution. In terms of commercial products, so far, as far as I know, there are several systems. So here we are not discussing about a material, but we are considering a component, so it goes directly in a system. And in that regard, the comparison, especially in price, it becomes way more delicate. System providers are very good in selling the entire package, but it's difficult to take apart the cost of the individual components. So in this case, a business development approach should be explored, and I have to admit that the research phase is still in action, and the business development part is ramping up. So far we cannot conclude anything. What we can build are just analogism and saying that everything that simply costs too much is not market ready. So be valuable must be within ranges that the market is willing to pay.
Okay, thank you. And
yeah, in our case, it's TRL7 in a former project, together with other technologies that are not the insulation. And yeah, we are in the process of comparing it to, because we worked in the past with this load-bearing sandwich panel and for a company, NTS in Italy, and compared to this panel that they had in their facilities that they produce on a normal basis, it was better because of the reduced weight due to the insulation, and also because we approach it with a external layer of textile reinforced concrete. Cost-wise, as Michele said, it depends if we sell only the insulation or it's like a full component. It's a different thing. We are now working on selling the insulation, basically, so that they can use it in prefab companies to implement it as they want. And as I said, in lab scale, pilot line scale, it's around 50 euros per cubic meter insulation. I think that on a production larger production could be reduced substantially. But yeah, these figures we don't have. So this is like the figures that we have for our production, that it is nearly, we haven't done it, but we can go to up to 5 cubic meters per day, something like that.
Okay, thank you, Miguel. And any more questions? Okay, so if there is no question, then sorry, I will. So thank you all the participants, and we will organize the webinar series continue next year for iClimaBuild, and you can follow us on iClimaBuild.eu or Facebook, Instagram, sorry, Facebook or LinkedIn and Twitter, and so I hope you are happy with our webinar, and see you next time. And yeah, you can follow our activities on the social media that I mentioned. And thank you very much for all speakers, Miguel, Agnese, and Michele.
Thank you.
Okay.
Thank you.
Okay.
Thanks.
And bye.
Bye bye.
Thanks. Bye bye.